Welcome back to the deep dive. Today we're tearing down something pretty crucial in the industrial world, the bag filter.
That huge piece of kit you see at power plants or factories.
Exactly. The unsung hero keeping the air cleaner than it otherwise would be. We're diving into the engineering physics behind how these actually work.
Yeah, the principles are quite elegant when you break them down.
So we've got some great source material guiding us today, and our mission really is to get beyond just knowing they clean the air. We want you to understand how.
Right. The flow, the particle capture, the cleaning, all of it.
We're going to try and unpack it so you really grasp the mechanics of this air quality management system.
And it's super relevant. I mean, these filters are everywhere doing a vital job. Understanding them shows some really clever engineering solutions to a tricky problem.
Okay, let's get into it then. First step, the contaminated gas stream. Where does it actually go when it first hits the system, before the bags even come into play?
Right, so the gas, full of dust and particles, comes flying in through ductwork. But then it immediately enters the main filter housing.
Which is big.
Oh yeah, much larger in volume than the inlet pipe. Think
Okay.
of it like a fast river flowing into a wide, calm lake.
Okay, so moving from a narrow channel to a big open space.
Exactly, and the physics kicks in instantly. Because the space is so much bigger, the gas velocity just drops dramatically.
Ah, okay, so it slows right down. What does that actually achieve at this stage?
Well, that sudden drop in speed is key. It basically robs the heavier particles of their kinetic energy.
So they can't stay suspended.
Precisely. They're moving too slow, gravity starts to win, and the larger, heavier bits just begin to settle out,
Huh. So they fall down toward the bottom.
often straight into the collection hopper below, yeah,
Hmm.
before the gas even gets near the filter bags themselves.
That's clever. So it's like a passive pre-filter, getting rid of the easy stuff first.
It is. It saves the actual filter bags for the finer, more challenging particles.
Right. Okay, so the gas, now minus the heaviest stuff, moves towards the actual filtration medium, these fabric bags. Tell us about those, woven, felted.
Yeah, they can be either woven or felted fabric, and they're arranged, usually vertically, in rows. The key thing is the gas has to pass through the fabric to get out.
And the fabric itself, that's what catches the particles.
It is, and it happens through, well, primarily three main mechanisms. It depends a bit on the particle size.
Okay, break those down for us.
So first, for the bigger particles still left, you have direct impaction. Imagine a particle heading towards a fiber in the fabric. If it's big enough, it just can't follow the air weaving around the fiber.
It just slams straight into it.
Pretty much, yeah.
Yeah.
Like a truck hitting a tree, it doesn't have the agility to swerve.
Makes sense. What about smaller particles that might, follow the airflow more easily?
Good question. That's where interception comes in. These particles might be following the streamlines of the gas around a fiber, but if the particle's own diameter causes it to just graze or touch the fiber, it gets stuck.
Ah, so even if it could flow around, it physically bumps into it anyway.
Exactly. It gets intercepted.
Uh-huh.
And then, for the really tiny stuff, the submicron particles.
The really hard ones to catch.
Yeah, we rely on diffusion. This one's a bit less intuitive. These particles are so small and light, they get bounced around randomly by air molecules that's Brownian motion.
Okay.
So instead of smoothly following the airflow, they're zigzagging all over the place.
Hmm.
And that random movement massively increases the chance they'll just randomly collide with a fiber and stick.
Wow. Okay. Impaction, interception, diffusion, covering all of the bases.
Right.
Now, here's where my sources suggested something really interesting happens. The particles don't just get caught. They build up, right? Accumulation.
Oh, absolutely. This is critical. Over time, all these captured particles form a layer, like a coating, on the outside surface of the bags. It's often called the dust cake.
The dust cake. Sounds unpleasant.
Huh, maybe.
Eh.
But here's the fascinating thing. Initially, this dust cake actually helps the filtration process.
Really? How does that work? You'd think more dirt would be worse.
Well, think about it. A brand new filter bag has pores defined by the fabric weave. But once that initial layer of fine dust builds up, it creates a much finer, more intricate filtration layer on top of the fabric.
Ah, I see. The dust itself becomes the filter medium.
Exactly. And this dust cake is often much more efficient at trapping those really fine particles than the original bag fabric was on its own.
So the dirt is filtering the dirt. That's kind of neat. But surely that can't go on forever. Doesn't it eventually clog everything up?
It absolutely does. That's the
Yeah.
downside. As the dust cake gets thicker and thicker, it becomes harder and harder for the gas to flow through it. It increases the resistance.
Oh, okay, resistance. And that leads us to a really important measurement, doesn't it? The pressure drop.
Yes, the pressure differential. or pressure drop. That's the difference in pressure between the dirty side, outside the bag where the dust cake is, and the clean side, inside the bag.
And as the cake builds up.
That pressure difference increases. The system's fans have to work much harder to push the same amount of gas through that thick, resistant layer.
Which means more energy consumption, right?
Massively more energy consumption.
Yeah.
And potentially damaging strain on the fans and equipment. So monitoring that pressure drop is absolutely vital. It's like the filter's health gauge.
It tells you when things are getting inefficient and expensive to run.
Precisely. When that pressure drop hits a certain preset limit, you know you've got a problem. The helpful dust cake has become a blockage.
Okay, so we have this inevitable buildup, and we have the pressure drop telling us, Houston, we have a problem. You can't just shut down a giant industrial plant every few hours to clean these things manually. So how does the system fix itself? How does it clean the bags automatically?
Right, that's where the clever automated cleaning comes in. The most common method by far is the pulse jet cleaning system.
Pulse jet. Okay.
Basically, the system uses blasts of high-pressure compressed air. This air is stored in tanks and then directed down into the filter bags, one row or section at a time.
Wait, you blast high-pressure air into the filter bag, the thing that's supposed to be filtering?
Yep, it's a very short, sharp pulse, though. We're talking milliseconds.
Okay, a quick burst, but still, high pressure onto fabric. Doesn't that damage the bags over time? Seems like there'd be a maintenance trade-off.
That's a really important point. And yes, there is. The bags themselves have to be made of tough stuff, specialized fabrics, often polymers like Nomex or others, designed to withstand thousands of these cleaning pulses.
So the material science is key.
Absolutely. Engineers are always balancing the filtration efficiency of the fabric with how well it holds up to the cleaning. A tougher bag might cost more initially, but last longer.
Makes sense. Okay, back to the pulse. What does that short, sharp blast of air actually do?
It creates a rapid pressure wave, essentially a shock wave, that travels down the inside length of the bag tube.
A shock wave inside the bag. And that affects the fabric how?
It causes the fabric to momentarily flex outwards, inflate slightly, and then snap back. It's a really violent, rapid vibration.
Ah, like snapping a towel.
That's a great analogy. That sharp flexing action is what breaks the bond between the dust cake built up on the outside and the fabric surface itself.
Okay, so the vibration shakes the dust cake loose.
Exactly. It dislodges it. And once it's dislodged, what happens?
Gravity.
Gravity. The now detached cake of dust just falls straight down from the bag surface into the collection hopper at the bottom of the housing.
Ready to be hauled away.
Right. For proper disposal, or sometimes even recycling, depending on what the dust actually is. So if we zoom out again, you have to picture this happening constantly. Filtration is ongoing, the dust cake is building up,
The pressure drop is being monitored.
and then triggered by that pressure drop, sections of bags get pulsed, cleaned, the dust falls, and they go right back to filtering efficiently. It's a continuous cycle.
And this cycle, how often it pulses, that's automated too.
Totally. The control system adjusts the cleaning frequency. It depends on things like, how much dust is coming in, what kind of dust it is, the gas flow rate from the plant, and how clean the air needs to be on the other side.
So it adapts. It's not just cleaning on a fixed timer.
Ideally, no. It cleans when needed to keep the pressure drop and therefore energy use within acceptable limits. It's a balance.
A real balancing act between filtering effectively and not spending a fortune on electricity or wearing out the bags too fast.
That's the core of it. Using fabric bags, letting that helpful then harmful dust cake form, monitoring the pressure, and then using those controlled shock waves to clean things off periodically, that's the working principle.
It really is a clever system when you break it down like that. Okay, let's quickly recap the key takeaways for you listening.
Good idea.
First, that initial slowing down of the gas in the main housing is crucial for dropping out the big stuff passively.
Right, using physics before you even hit the filters.
Second, that dust cake paradox, how it helps filter better initially, but then becomes the main source of resistance.
The necessary evil, you could say.
Third, the pressure drop. That's the critical number telling you how the system is performing and how much energy it's guzzling.
Your main operational metric.
And finally, the pulse jet, cleaning that sharp shock wave, snapping the cake off the bags to keep the whole thing running continuously.
The reset button.
Exactly. It's quite an elegant solution to a very dirty problem.
It really is. And maybe a final thought to leave you with. Think about the fabric itself. The engineers have this constant tightrope walk.
How so?
Well, you want a fabric that's incredibly efficient at capturing tiny particles, which usually means a very tight weave or dense felt. But The tighter it is, the faster the pressure drop builds up, meaning you need to pulse clean it more often.
And more cleaning means more wear and tear on those expensive bags.
Precisely. So they have to find that perfect balance. Effective filtration versus bag longevity versus cleaning frequency. That trade-off, hidden in the material science, is really the silent engineering challenge behind keeping industrial air clean day in, day out.